In this online lecture, we're going to look at oxidative cleavage of alkynes and how we can use alkyne anions as nucleophiles. In oxidative cleavage, you're cleaving the triple bond and the remaining carbons are oxidized to the highest state possible. So if it is a carbon in the middle of a chain, you end up making it into a carboxylic acid. If it is a carbon that is at the end of the chain, you're going to turn it into carbon dioxide and it bubbles out and you lose it. The conditions can either be potassium permanganate and acid or ozone. With alkenes, potassium permanganate will take an alkene, cleave an alkene, and take it down to a carboxylic acid, but ozone, if you treat it with zinc and acid, will take it to ketones or aldehydes. That does not happen here with oxidative cleavage. Regardless of the circumstance, you take it down to a carboxylic acid. Notice that if you have a terminal alkyne, you basically are taking away one carbon when you do oxidative cleavage. So if you're wanting to shorten a chain by one, it's a useful method to change the end of the chain to an alkyne and then do oxidative cleavage. So here is an example with ozone. You can see that ozone here is taking this terminal alkyne and changing the carbon that is on the end into carbon dioxide, and the other carbon is changed into a carboxylic acid. You would get the same results with potassium permanganate and an acid. Below that you see an internal alkyne. What happens? Both carbons are changed to carboxylic acids. And again, you would get the same outcome with ozone. Here's an example. This alkyne has a carbon attached to a benzene ring, so that turns into benzoic acid, and the other carbon, which is terminal, ends up being carbon dioxide. Whereas in the example below, what would happen? You would end up making acetic acid from the half of the alkyne that's on the right, and the other half of the alkyne on the left is turned to benzoic acid. And again, the conditions that you need for this are either ozone or potassium permanganate and acid. So how can you make acetic acid from 2-chlorobutane? You cannot do it in one step. Write down 2-chlorobutane and try to figure out how you can make acetic acid from that. Well, to make acetic acid, what you have to do is the first thing you're going to need to make an alkyne. You know that because we're in the alkyne chapter. 2-chlorobutane can be eliminated to form an alkene. Once you have an alkene, you can treat that with bromine or chlorine to give the vicinal dihalide. Once you form the vicinal dihalide, you can treat that with base to give the alkyne. Here, this is butane. Butane can then be cleaved with ozone or potassium permanganate and acid to give you acetic acid. Notice, because this is 4 carbons and we cleave down the center, you would make acetic acid from this side and you would make acetic acid from this side. So for every 1 butane, you would make 2 acetic acid. So how can you make this diacid from any alkyne? Well, right off the bat, do you notice there's a carboxylic acid here and a carboxylic acid here? Well, 2 acid functional groups can come from an alkyne. What if you connect those 2 carbons? If you connect those 2 carbons, it could come from this alkyne right here. See, there's 10 carbons altogether, and if I count these, you will see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All you'd have to do is add something that would do oxidative cleavage like ozone, or you could use potassium permanganate and acid. Alkynes, if they're terminal, can be deprotonated with very strong bases. The acidity of an alkyne hydrogen, so we're talking about a terminal alkyne like this. This hydrogen here has a pKa of about 25. So if you get a base that has a conjugate acid that is weaker than a pKa of 25, you will be able to deprotonate this terminal alkyne. An example is sodium amide. Ammonia, the conjugate acid of sodium amide, has a pKa of 35. So it is a weaker acid than the alkyne, so its base is strong enough to deprotonate that terminal alkyne. And what you get, you remove a proton, make ammonia, and look at this anion. This is relatively easy to form compared to other hydrogens on carbons being removed, because this negative charge, the 2 electrons that form that negative charge, are held in an sp orbital, which holds it in a lower energy than either sp2 or sp3. That is what makes this hydrogen over here acidic enough to be removed with sodium amide. This anion now can undergo some reactions. This is an excellent nucleophile because the carbon with a negative charge on it has that non-bonding pair sticking out linear it's a linear molecule, and so the non-bonding pair is 180 degrees away from the triple bond. So this is like a little bullet, and it can dive into places that are kind of small, as in an SN2 reaction. So here is this good nucleophile diving in to a carbon and pushing away a leaving group. Of course, you're going to get inversion because this is SN2. So the nucleophile comes in and pushes off the bromide. And there you see the inversion occurred. So for you to have this occur, the carbon here must be primary, and you have to have a good leaving group. So either a bromine or an iodine leaving group is important so that the nucleophilic displacement is fast enough and the competing elimination reaction does not occur. If you have a secondary carbon, or if your leaving group is not very good, what you're going to get is elimination occurring instead. The net effect is that you add this carbon chain to a substrate. So the substrate here, where the R' is written, basically is added onto a terminal alkyne. So what do? You take the terminal alkyne, you treat it with a strong base like sodium amide, and then afterwards you mix the substrate with it. And the alkyne anion then does SN2 on the substrate. Here is an example. You have propyne treated with sodium amide. That forms the anion, which then can do SN2 on this primary alkyl halide. We end up getting the carbon triple bonded to the carbon, then with a methyl attached, being attached to the carbon right here. So this carbon is this one, and then here's the ring, here is the ring, and then here's the propyne that did an SN2 on the carbon right here. So now, with your new knowledge, determine how you can do the following. First of all, how can you make 3-No-9 from any 6 carbon or less compounds? So how can you make 3-No-9 from any 6 carbon or less compound? Well, 3-No-9, you know, you could make with an alkyne anion, because that would take an alkyl halide and an alkyne that you change into an anion, a terminal alkyne, and then you could join them together and make a 9 carbon chain. So what could you start with? Well, because it says 3-No-9, you would have to have 4 carbons with a terminal alkyne. What would you use? 4 carbons and a terminal alkyne. If you treat this with a base, now all you have to do is the anion would be here, and then you have to figure out how many carbons you would need to have a 9 carbon chain. Since there's 4 here, you would have to have 5 carbons in the substrate chain. So 1, 2, 3, 4, 5. So I would use pentyl bromide or bromopentane, 1-bromopentane. And this would end up doing an SN2 on this carbon and making 3-No-9. How can you make hexanal from 2,2-dibromohexane? Well, the first thing you would want to do is write the 2,2-dibromohexane down, and you'll see it's the same number of carbons, so you're not cleaving or adding carbons. I know I can go through a alkyne intermediate, and if it's 2,2-dibromohexane, I can treat with base, which gives me 1-hexyne. 1-hexyne can then be treated with borane and hydrogen peroxide, and that would give us an aldehyde. I'm going to show you the reaction in just a moment, but I want you to stop and realize I'm giving you one way to do this that makes a lot of sense, but there may be another way to do it that you've figured out, and just because your idea isn't the same as mine doesn't mean it's necessarily not going to work. So if you do come up with something that's different from mine and you have any questions, go ahead and ask me to look at your synthesis to make sure that it is correct. So here is the 2,2-dibromohexane, and we can treat it with strong base. You actually then have the 1-alkyne. The 1-alkyne can be treated with borane and hydrogen peroxide, and it gives us the aldehyde. Remember the oxygen on the less substituted carbon when borane is involved. How can you make hexanoic acid from 1-bromopentane? Well, right off the bat, you should see pentane is 5 carbons and hexanoic acid is 6. So we're going to have to get another carbon on there somehow. Let's go ahead, and 1-bromopentane can be treated with an alkyne. That's going to give us heptyne, 1, 2, 3, 4, 5, 6, 7 carbons. Well, that's not hexyne. We need to remove one of those carbons. So what I can do is do oxidative cleavage with ozone, and that's going to give us the carboxylic acid. You might have had trouble figuring this one out, but remember, every time you see hexanoic acid, remember that can come from oxidative cleavage. And so if you think about it, to get hexanoic acid from oxidative cleavage, you had to have had a minimum of 7 carbons. So that would be heptyne. And then you might have been able, I don't know if you would have figured it out, but you could look at 1-bromopentane and say, oh, well, if I use an acetylene anion, that would add 2 carbons, which would give us just the number that we need for oxidative cleavage to give octane from 1-pentyne. Well, again, the first thing that you're going to do with this is you are going to count the carbons and see 1 pentyne and N-octane. There's 5 carbons in the starting material and 8 in the final material. N means it's a straight chain. By the way, it stands for normal, and it's a straight chain. So if I'm looking at 1 pentyne, I know I need to add 3 carbons to it. If I make that into the anion, I could actually use propyl bromide, and that would then give us 3 octyne. So here's an example. 1 pentyne treated with sodium amide and then with propyl bromide gives us, not 3 octyne, but 4 octyne. 4 octyne then can be converted to the alkane by hydrogenation. And notice this is a regular catalyst, so it takes us all the way down to the alkane. If it were a poison catalyst, it would take us to the cis alkene. So this is what you need to remember, is that alkynes can be converted to ketones, aldehydes, dihalides, vinyl halides, alkanes, and you can cleave them to 2 carbonyls, or not 2 carbonyls, 2 carboxylic acids really. Remember, that gives you a shorter chain. And if you're trying to make an alkyne, remember those can come from alcohols, halides, and alkenes. And so now try to think of functional groups as being items that you can modify to get other functional groups. Keep that in mind as we start going through these chapters so that when you're given a synthetic challenge, you can think it through. And the best way to figure these out is to try several problems and start learning how to think them through.